first lecture on EM, I explained the theory or the principle behind EM. Okay? And I took this example. So I have a two-dimensional plot of the data with the class labels. Class labels given by the red, green, and blue color. Okay? So in the left-hand side, I have the class label, and I'm trying to model the distribution of the data by three Gaussians. Okay? Each of the Gaussians will belong to each of the labels. So there'll be a Gaussian on this one, Gaussian on that one, and Gaussian on that one. And I'm going to model the distribution as a Gaussian mixture model. Okay? Gaussian mixture model meaning that it's composed of three Gaussians linearly weighted. And on the left-hand side, it's easy because you just find out how many reds, how many greens, how many blues there are. Also, I gather for estimating the parameter regarding the red one, I just gather the red ones and I estimate the mean and the variance in estimating the Gaussian for that one. And I could do that for the green one, and I could do that for the easy on this side. Okay. And on this side, I have no color. I have no labels where to tell me which Gaussian it came from. And I'm trying to model with three Gaussians. So the principle behind EM is to define a random variable or variable, okay, probabilistically, which means a random variable, that will tell me what the probability of it being red, probability of being red, probability of being green, and probability of being blue. So for each of the things. And then, so for each of the data here, I would define something like this. And then based on that, I would estimate the mean and variance for each of the colors. Okay? And then once I have that, then I can estimate this parameter. So once I have this, I can estimate the parameters, theta. Once I have the theta, then I can do that. And I go back and forth. It's an iterative process. Until there is no update. And so that's what EM is related to this particular problem. Okay? Defining this variable, which will help me make the problem easy. Okay? So let's look at some, back to the slide. So here is one-dimensional data. One is distributed by this red thing, and the other one is by this blue thing. And the probability that I choose the red one is pi, and the probability that I choose the blue one is 1 minus pi. And once this red is chosen, so that's represented by c equals 1, then if it's red one, then I can sort of define what the probability of the value is for the x. Okay? And usually, in this example, I'm going to assume that this is going to be a Gaussian. Okay? For this example. Okay? And let's say, so the probability that I choose blue is 1 minus p. And once blue is chosen, if it's given, then then the probability of x is defined by this other Gaussian. Okay? So the probability of x, given all the parameters, pi and the mean and variance of the red one and the mean and variance of the blue one, then the probability distribution can be written like this. Okay? So of the pi, the probability pi, it follows Gaussian 1. With probability 1 minus pi, it follows Gaussian 2. Okay? So this is a two-step process. So you throw a coin with probability head of pi, tail 1 minus pi. You throw it. If it's head, then I choose this Gaussian. If it's tail, then I choose this Gaussian. Okay? And so this is a one-dimensional representation of that. And this is sort of mathematical. Pi stands for probability of being class 1 or the red one. 1 minus pi will be choosing blue one. And if it's red one and you're given all the parameters, then the probability of x follows this is represented by Gaussian. And if the blue one and all the parameters are given, then the probability of x will follow another Gaussian. Okay? And this is called the Gaussian mixture model. Gaussian mixture model. Okay, and here I have mixed two Gaussians. Okay, and I can, in general, I can mix m Gaussians. Okay, and what are the parameters in this case? Pi, the probability of choosing the red one, mean and variance of the first and mean and variance of the first Gaussian, mean and variance of the second Gaussian. That's the parameter. Okay. Here's a little bit more probability of choosing this Gaussian as opposed to this one will follow a Bernoulli process, a Bernoulli distribution. So Bernoulli with probability pi, choose 1. With probability 1 minus pi, it's choosing the blue. Okay, and we often say this is also a generative model. This is how the data is generated from this probability. Okay? It's generated by this distribution. So you may say, okay, so usually the setting is you're given n training data, how do you get theta? Okay? So that's the setting that we like to do. And you can think of solving, maximizing the log likelihood. We want to estimate theta such that the probability of the observation is maximized. Or we could put a log there, okay? Because log is a monotonically increasing function. The position of the maximum doesn't change. So if you do that, you get that. And you try, so in the normal setting, how would you find this theta? How would you find theta? To maximize this likelihood, if I'm doing maximum likelihood, estimation of theta. How do I do it? I take the derivative with respect to theta, and then I try to set it equal to 0, and then I find theta, right, that does this. But you try doing this. Difficult. Impossible. So one way, when this is difficult, is use gradient descent. Okay, this is an algorithm that is used very often in machine learning and many algorithms. And let me just tell you how this algorithm. So what I'm trying to say is taking the derivative and setting it equal to 0, finding the parameters that would make this thing equal 0 is difficult. You try it, okay, at home. Take the derivative of this and try to set it equal to find the theta. Difficult. So the way you do this is through this. This is gradient descent or gradient ascent. So you start at some position theta I. Okay, theta I. It's the ith step, or just forget about this. You initialize your theta. You initialize. Oops. You initialize your theta to theta I. Just some number. You just give all the values something, theta I. Okay? But you know it's wrong because you just guessed it. The probability of getting it right with your guess is probably 0. So you guess it. You take the derivative of this law. This is the derivative with respect to theta. Okay. Now, what does this derivative say? It's a gradient. Which way is this gradient pointing? Which direction is this pointing? It's a vector. Which way is it pointing? It's pointing towards the direction where L theta is increasing. Okay? That's the direction that it's increasing. I'm here, and this is the direction that it's supposed to increase. So I'm going to move my point in the direction of increasing likelihoods. Okay? And how much should I go in the direction of increasing likelihood? Don't know. Mu. Okay? I go in the direction mu times that. And that's how you update your theta, the next step. Okay? And then you do that again. You put this theta I plus 1. You take the derivative at that point. Actually, this is what you should do. There's a notation missing. Theta has to equal to theta I. Take the derivative at that position. And then you keep on iterating. And hopefully then you will climb up to the top. Okay? So this is gradient descent. Instead of doing it this way, finding the mu is not an easy problem. Usually there are many methods for determining mu. You first take a big step, and then as you go, as the iteration increases, then you take smaller amount of steps, and there are various ways. Okay, but difficult. This slide is about if you know. This is the left-hand side of this previous. If I have this situation, how do I calculate my pi, mu's, and sigmas? Okay. You just, let's say for red one, you just count the number of times that it's read out of all the data. You just average all the data that is read, okay, divided by the number of reds there. Variance, for each of the data, each of the data that is read, you subtract off the mean, take the square sum, and then you take the average, and so forth. And you can do that. So this is given the cluster label, and I call this to be clustered. Now, EM, what I was going to say that I told you the principle or the philosophy behind it, and this is the general idea. Here it is. You make an initial guess of the theta. You make an initial guess of the probability of the mean value, variance, and also the mixture probability, the pies, or the probability of being red, blue, and green, and so forth. Then you compute from this. You can compute for each of the data. What? So given xi, you've already made an initial guess of what the parameters are going to be. Okay? Initial. Then from that, you can find out what the probability of this data being class 1, blue, or red, and green. You can find all that. And that's what we call gamma I. Okay? And this step is called expectation. Okay? So in my previous slide, right here, finding this. What is the expectation of being this dot being red? What is the expectation of this dot being green? What is the expectation of that dot being blue? Okay. And I should also be more exact. I should say this as x out here. Okay. That is the expectation step. What's the expectation of the latent variable? And then based on this, I have to update my parameter. Okay? And I update the parameter by looking at this equation. The probability of the data. So now I have this is the previous parameter. Okay, the parameter should I should have bar here. 여기 bar 좀 고쳐주세요. Yeah. Bar here. Initial guess bar. Okay. I have the data, and I also have the corresponding class. Okay? I don't have the class actually. I have, what do I have? I have the probability of being each of the classes. So this is all the data. C is, I can say all of the data are red. All of the data are red. Only one is red, and I can have different combinations for each of the C's. All right? So if I had two points, this is data x1 and x2, and this is the probability of, let's say class is 1 or 2, so it's going to be 1 or 2. Then I have probability 0.4, that is class 1, 0.6, class 2, that one, 0. Let's say 6 here and so forth. So I'm going to consider in this thing, what is the probability of the first data being class 1, first class being 1, second class being 1, and I also have the data x1 and x2. Then I could also probably calculate x1 being 1, x2 being 2, and x3 being x2 being 1. And so forth. I could have 4 combinations for this, right? The other one is C1 equal 2, C2 equal 2, X1, X2. So there are four possible things, okay, for this example that I gave. Then I'm taking the expectation of this probability, joint probability, over this probability. What is this probability? Given the parameter, so here in this case I should, actually, sorry, all the bars should be removed, and I put a bar right here, or it's either way. No bar here. So all the bars are moved, all the bars. So the initial guess is theta, theta, and theta. We also have this probability. So what is the probability of being C1 equal 2 times probability C2 equal 2 given theta and x1 and so forth right here. So I multiply that, multiply by PC2, C1 equal 2, C2 equal 1, theta, x1 and x2. By the way, the theta is the initial guess. This is the guess. So I could do that for that one also, probably for that one. That will be writing this expectation of this over this, writing it out in 4 terms. And then I would have plus. This whole thing will be that, right? So I considered all the combinations of C, all the combinations, 4 combinations for this example, over this probability. What's the probability of being this? Each of them are weighted by that. And then I take the sum. That is the expectation. This number, theta, given theta here without the bar, is my theta, initial guess here. So based on that theta, I could calculate what the probability is. Okay? I could calculate that probability. Theta, I don't know, let's say. This is the theta, this is theta bars. And what I do is I want to find a theta bar that would maximize this thing. Yeah? Make that a function of theta.
세타랑 세타 바가 뭐가 다른가?
다시 얘기하겠습니다. 세타는, 여기 세타는 위에서 가정한 세타가 되겠고요. 오케이? 세타. 오케이? 이건 알고 가정한. 틀렸지만은 가정한. 그래서 다양한 클래스의 확률을 알 수 있습니다. So, 이거는. And this is for some, this is going to be a function of theta bar. Okay? I want to find a theta bar that would maximize this quantity. Okay? So this is, I'll say it in words, probability of the complete data. We call this complete data. Data with its label. Well, but the label can be anything. Probability of the complete data over the parameters that we need to estimate, given that the the probability of C, probability of C is based on your initial guess. So theta는 여기는 알고 있다고. 그러면 C는 여기 다양한 C가 있을 수 있는 C가 가질 수 있는 다양한 그 확률은 알고 있어요. Okay? We want to maximize this one, which is the expectation of the complete data. We call that complete data over the probability of the class. So we call this the latent variable.
근데 P의 C랑 D의
어디?
그 옵티마이제이션 바를 옆에
여기?
네, 그 D가
D?
D는 랜덤 베리어블 저기서 그냥 값인가요? 내가 알고 있는 값인가요? 아니면 D가 의미하는
D는 is training data.
그런 값인가요? 알고 있는
I know the training data. 트레인 데이터는 갖고 있잖아. 네. 그렇지만은 거기에 해당되는 클래스의 확률은 모르잖아.
네, 그 D가 알고 있으니까
뭐를 알아?
D가 지금 트레이닝 데이니까 제가 가지고 있는 거잖아요. 지금. 그러면 D를 뭐 기분으로 놓지 않고 확률적인 저 값에 대해서 좀 이해가 안 돼서
이걸 뭐라고 그래요? 제가 처음 렉처에도 얘기했는데 이런 것들을 뭐라고 하냐? What do I call this type of thing? Parameter and the observation. What do you call this? Likelihood. Okay, this is just the likelihood of the complete data. All possible. So I know this is fixed. This I could put in. Okay, all possible value for the colors or the latent variables. And it happens with this probability. 무슨 말인지 알겠어요? 다시 한말로 할게요. 세타 이것을 최대치로 만드는 요것을 최대치로 만드는 세타 바를 찾을 겁니다. likelihood처럼 우리 maximum likelihood 할 때 파라미터가 주어졌을 때 데이터의 확률을 최대치로 만드는 세타를 찾잖아요. likelihood처럼. 이런 식으로 씁니다. 데이터는 주어졌어요. 이 C는 몰라. 근데 C는 우리가 모든 경우를 다 생각하는 거예요. 여기에 합당한 모든 경우를 다 생각하는 거예요. 그리고 이것이 일어날 확률은 뭐예요? 어떤 특정한 C에 대해서. 첫 번째 거는 레드고 두 번째 거는 파란 거고 뭐 세 번째 거는 파란 거고 이렇게 주어졌어요. 이게 어떤 확률로 생길 수 있어요? 이 확률로 생길 수 있죠. And this step in updating, maximizing, this is called the maximization step. So expectation and maximization, you take the E and M, and you call it the EM algorithm. Okay? Now, but this is, so that, and then your theta hat, the circumflex will be your view guess of theta. And then you go through this thing over and over. What I could have done, so this is maximum likelihood. So if I do this iteratively and find my solution, my theta, my ultimate theta, okay, EM, then this will have maximized this probability. Okay? Which we were initially trying to, maximum likelihood. Okay? So this, if I go through this iteration, it will have maximized, you would have arrived at my maximum likelihood solution. Okay? Maximum likelihood solution. Now what I could have done, I could have done this. Instead of doing that, I could do this actually. I could have done that. Okay. Oh, this is no, this is still theta bar actually. I could have added a bias. Yes, I could have done that. I could have done this as well. Theta bar here. Okay. And that way, if I do this, then I would have to, I'm assuming I have to define this p theta probability. Okay. And this will be a maximum a posteriori solution. Okay, but if I do this, just do this, I'll be arriving at the maximum likelihood solution. Okay, so here is actually what is. So I have now only red and blue. Red and blue. Two labels, not this other color. The previous example had red, green, and blue. Let's assume that's only red and blue. So what have I done? I've made an initial guess of what the theta value is. Initial value of theta. So here is data, this green thing, without any label. And my initial guess of theta is this. This is blue thing and red thing. What does that mean? Initial guess is this blue thing and red thing. What does that mean? 그러니까 어떻게 잡았다는 얘기죠? 이렇게 동그라미 이렇게 잡았다는 게. 이게 퍼레미터가 뭐가 있다고 그랬어요? 파이 있다고 그랬고, 그 다음에 mu1, sigma 1, 아니, variance 1. Variance 1, mu2, and sigma 2, right? So, I've said, these, look at the circle, it's the same size. So I've said, probability of each one is 1 minus pi, 0.5. Both of them are equal likely. Where is mu1 and mu2? Right here, right here. That's mu1, and that's where mu2 is. Okay? Where is sigma 1 and sigma 2? That's probably in this direction. mu2. It's a diagonal. It's a circle, so so I should write it this way. It's a matrix, both of them, you know, 1, 1, 0, 0, 1, 1, 0, 0. Okay? The same size circle. That's my initial guess of that. Okay? Then based on that, based on my sigma, hey, look at the colors of the dots. What does this mean? What have I? Some dot is like mixture of blue and red. What does that mean? What have I found here? I'm looking at gamma here. Gamma of each of the data. Let's say this is data 1. Gamma 1. That's the nth one. That's the nth data. Then it's gamma n. What does this gamma represent? What does that gamma represent?
세타랑 데이터가 주어졌을 때 파라미터의
저 확률 아니야.
그래서
그렇지. What is the probability for this one? What is the probability? Let's say, look at that one. Probability of being read given the data x, n, and theta. Probability of blue and x and theta. But I don't really need to define this one. Why? 요거 하나만 정리하면 돼요. 이거는 필요 없어. 왜? 요건 1 마이너스니까 요거 하나만 갖고 요거 나타낼 수 있어요. 그렇죠? 요거 주어지면 요거 구할 수 있어요. 어떻게 구하죠? 요거는 어떻게 구하면 되나? Probability of red and probability of blue. 어떻게 구하면 돼? xn이 주어졌고, 세타 값이 다 주어졌어요. 우리 뭐 이거 다 정해놨잖아. Probability of red를 어떻게 구할 수 있어? 이 가우시안이 만들어졌을 거 아니에요, 그렇죠? 가우시안 만들어졌어. 그러면은 여기의 확률을 알 수 있어, 없어요? 네? 확률을 알 수 있잖아요. 여기서 여기의 확률. 그 다음에 또 여기 오는 또 확률도 알 수 있지. 두 개의 확률이 또 더해가지고 1이 되는데 지금 1이 안 돼. 그래서 normalize. red를 위에다가 분자에다 하나 갖다 놓고 밑에다가 둘 다 더하면 뭐 나오는 normalize 하면 나오고. 무슨 말인지 알겠어요? 이게 정해졌기 때문에 여기 가우시안의 형태는 알아. 그럼 어떤 위치, 내가 위치는 정해졌어. 그럼 위치에서 내가 빨간 확률, 파란 확률 각자 이러니까 내가 어느 정도 레드고 어느 정도 파란 걸 알 수 있는 거야. 다 알 수 있죠. 그래서 각각 색깔을 줬어. 오케이? So once I have this, what can I do next? 이게 다음에 이게 다 그 클래스의 확률을 또 나눠줬어. What can I do that after? This is, what do we call this step right here? Expectation step. What about the next step I've done? Maximization. What have I done here in this case? The previous slide will probably tell you how to do this, but just in principle, it all boils down to this. Now I have to update this thing. I gather all the blue ones. I gather all the blue ones. And even this pink one will have that proportion of that data coming in. For an evaluate blue. Then I can calculate the mean and the variance again. And likewise for the red one. Okay? That's what's going to boil down to. I'm doing this. 요거를 하고 있지만은 이거 실제로 다 풀이해보면은 결과적으로는 각 클래스에 대해서 클래스에 해당되는 데이터만큼 모아가지고 mean 값을 구하고 variance 값을 구하는 거예요. And that's how I update it. Understand what I'm doing? Right here? This is for, so that's expectation maximization step. And then I do this thing 2 times, 5 times, and then after 20 times, I've arrived at that. Okay. This example, EM is not only to find Gaussian mixtures, but it's used in many, many different scenarios. Okay? Not this right here, by doing that, I have arrived at the maximum likelihood solution. But if I add a bias, I could arrive at maximum a posteriori solution. Okay? This is a very general algorithm for anything. Not for anything, but I mean. Okay. About initial guess. How should you start? Well, usually, pi, you give an equal value to each one of the things. Or better yet, actually, equal. It's uniform. Blue, red, green, all equal. And then set each of the variance, if you're doing Gaussian mixture, to be the sample variance of, regardless of whether red, blue, or green, you just take it and you look at the variance. That's a good initial point. Okay? And the mean, you just take the sample, you take the mean. Okay? Or you just pick 2 points and you call that the mean. Just pick 2 points and that's mean. That's a good initial guess. Okay, so let's look at gamma. If you look at gamma, it looks like this. Look, if the 2 Gaussians, one is for red, that one. This one is for red one. That one is for blue one. Okay, and I have the theta value. So I have these theta values, and I'm looking at point xi. Well, this gamma I says, what's the probability that it's red? Okay, so it's probability of red right here divided by probability of red, probability of blue with this proportion. And then I put also the proportion of the red. So this is the probability of red, and it makes sense. Okay. And maximization, remember we have to solve this one. If you go through all of this, you arrive at this. Let's say from mu. So I've found gamma for each of the data. How much is it red? How much is it going to be blue? Let's say gamma mu1 is the mean of the red one. So for each of the data, I take this proportion, okay, which says this is the probability of being red. I multiply it for all the data and normalize it by its probability of being red. Okay. So it makes sense as well. And you can do that. Variance is this way. Now, this EM looks very nice. Okay? But this algorithm has been around for a long, long time. We think it's a very nice algorithm. But we don't like to use this in machine learning, okay? Because it overfits. It has some very bad properties. And this is the reason right here. And let me show you. Do I have this picture? First of all, I want to ask you, it starts with an initial guess, and then you do iteratively to find the solution. That solution is actually not the maximum likelihood estimate. If there is a unique solution, if it's a unique solution, then it's a maximum likelihood estimation. Let's say there is no unique. Okay. Is this, does it give you a global, so I'm looking at this. maximum likelihood. This is maximum likelihood. Okay? Let's say this is very, very complicated. We'll go through this. The EM. Does this give you a global maximum if I go through this? So I start with some initial point and I go through this. Is it going to give you a global solution? No, it doesn't. Okay? It's only local. Okay? So you have to try with different initial points. Okay, so that's it's a global, local optimum. Another reason, as I said, it's overfitting. Where's this? I erased this. Sorry. I want to find theta that maximizes the data. Okay, the probability of the data. And let's say I have one-dimensional data that's scattered around here. Like that. And I want to fit two Gaussians on it. Okay? What is one solution that gives you a really big one like this? One, so you want max, so I want to put two Gaussians, let's say, two Gaussians on these data, X, one-dimensional data. I want to find the parameters to do that. Give me one case where this will be very big. Give me one case that I really would not want, but it gives me a big value.
The two Gaussian distribution from left one with a broad one, the right one with a sharp one.
Not only sharp one, but let's say I fit one data on that one. And the variance is 0. Okay? It's just a delta function. That's infinite. And then I have the other one looking like that. What is this probability? What is this probability? How would I represent this in another way? 이걸 어떻게 나타내지? D라는 것은 데이터예요. 이거죠, 그렇죠? And I know that this is all given. How can I write it another little way? What would this be? Usually in the machine learning setting, we assume each of them are what? Independent. So what do I write it? How can I write it? Probability of each of the ones given theta, like that, right? So this one would have some finite probability, one finite probability under this Gaussian. So all of that multiplied by one of them, which goes to where? Infinite. One of them will be infinite. So what would happen? But I'm maximizing. That's one way of maximizing. Is that good or bad? That's bad. That's overfitting on one of them. Okay? And that's not what, it's not what you want to do. Okay? So EM can overfit. Some properties of EM, we'll go through some of them. Theta was some, our estimate at some ith step. Okay? Theta prime was my updated one. Well, what happens with EM? This happens at each step. If I have my initial guess, given that probability of data, is lower bounded by my update. So at each step, what's happening? My likelihood is always increasing. Increasing or staying the same. Okay? So it's monotonically improving. And it's generally better than gradient descent or gradient ascent. Okay, I've explained what gradient ascent. You want to go in the direction where the likelihood is increasing. That's the problem. It's easier to implement EM than this, and it's faster. Oh, it's slower at the plateau, meaning at the top. Once you reach very close, it's easier than gradient, but sometimes slower. Okay, EM is a little bit slower on this as you go towards this than gradients. Okay. So there are other properties that I really don't want to go in detail. Okay, let's try it. 이 다음 강의도 준비가 돼 있어.
네.
뭐죠 다음이? 그래프.
네,
Okay, well anyways, okay, now I'm going to change notation, sorry about this. I'm going to use H instead of C. Okay, to represent that it's hidden. Okay, it's a hidden Z we don't know, the C we don't know. It's hidden. Probability of the hidden. Probability of the class given data and theta bar. What do we call this? What was this? What do we calculate this? When do we calculate this in the EM? It's the E step, right? The E. This is data and some estimate of theta, probability of H. You can write it this way. So you may say, how did you get that? This is very easy again. What's the probability of H and this using Bayes' law? It's the joint probability divided by theta, like that. But we found that we are all given, there is the world. The world. The world is given. Oh, we forgot to include the world in there. There you go. Okay? And that gives you that. So you're rearranging, putting this up here, putting that down here, leads to that. Okay. So this is what we are trying to actually maximize, right? Probability of data given theta. But on the right-hand side, we see what? What's in the right-hand side? Something that did not appear on the left-hand side. It's the hidden thing. Okay? So we do that. Or I could take the log of this thing. Log of that. So the log of this, log, subtract log of that. Okay? So log of that. Now, what am I trying to do? I want to maximize this with respect to theta. And this is the notation that I use. And then what do? On that equation, I put expectation on the left-hand side. So remember I had log of theta must equal log of, let's see, let's get the C theta H D minus L H theta H of D. That was from the previous slide. Then what do I put? I put expectation of this over P over H given d theta on the whole thing, all equations. Okay. Now, what's the expectation of this over H? What's the expectation of this over H? This one does not have any H value. So expectation of something over H. So it's going to be just that. Okay? That's going to lead to that. Expectation of that is that and that. Okay? So in the previous equation, I've just put expectation. Okay? Then I'm going to call this side the Q, and this I'm going to call it R. And this is going to be often called the auxiliary function. Auxiliary function. Okay? Then I'm going to subtract two things. One, theta star. This is where it's maximum. This is just some other theta. Okay. I do that, and I find out that this is always negative, okay, by some Jensen's inequality. We look at the back side, and it really turns out we need to maximize over the auxiliary function. Okay? So you need to maximize. So what I'm trying to say, go through it. This all boils down to, so I looked at L theta star D and theta D. Okay, this is where this L star makes this thing maximum, let's assume. So I want this thing to be positive. Okay? So the other side, the next slide, will tell you that this is always, if I subtract that, if I subtract these two, it's always negative. So I got a negative, negative. So I don't really have to worry about this. And it really turns out that if I maximize over this, so if I want this, I need to have, I'll write it down. Just so that. Down to this, I want this to be positive. Okay? For this to be positive, this has to be positive, which means that I just maximize this. What do we see this? Maximizing this? 어디서 봤죠? That is the maximization step. That's the maximization. So I've derived EM for you. Okay? Go through it, read it. And these are some other comments about Jensen's inequality and some more other various examples in the back. Okay? Worked out examples. And I'm done with EM. Okay? So, a little bit of introduction. What is EM? EM is an iterative way of finding the maximum likelihood solution. Or it could be used to find the maximum a posteriori solution when you take the derivative and taking the derivative equal and setting it equal to 0 is difficult. Okay? Then you may do EM. And we looked at example for Gaussian, two Gaussians. And we looked at the mixture 2 case. Okay? And we also looked at the case where the labels were given, blue and red and so forth. And we found, relating this, we looked at this, and then we removed the cluster label. Okay, we removed the cluster label to arrive at the general solution for EM. Initial guess, expectation, maximization, some properties, and there are some examples given to you at the back of the PowerPoint slide, and I also derived EM for you. Any questions?
How would be different from, for example, K-means clustering of the signal?
It's based on totally different thing. Here, I'm trying to, I can fit a distribution over the clusters. Okay? I can fit a distribution over the clusters.
There is no
Pardon?
in K-means there is no such distribution.
Distribution here. But it could be, so in K-means, let's say in K-means, usually you do Euclidean distance. Okay? Nearest. What if I do a Gaussian on the clusters, and I use this type of thing? This Gaussian says this, okay, normalizing thing. I'm putting an exponential on the negative of the distance metric. See, clusters, you can make it similar if your measure in clustering is this. Okay? So you could be talking about the same thing, but this is more in a probabilistic way. You understand what I'm saying? 질문 또 있나요? Okay, so these are some old methods. Okay. Now I'm going to move on to something that is relatively less old, but this makes this topic makes machine learning machine learning popular, and this makes machine learning really powerful. And it's one of the center ideas of machine learning. Okay? Machine learning, I've already said, it's based on Bayesian. It's a philosophy on prior and having the likely data observation. We looked at various distributions, conjugacy and all this, okay, and how parameter updates and that. We looked at, if we don't have probability, we can estimate it from the data. How to estimate the parameters, hypothesis. Now, at the core of machine learning is graph models. How do you represent probability or in terms of graphs? Very, very important. Very, very important. Some of these ideas have been around for a long time, but it wasn't used. It wasn't really popular. But now everyone is using graph models. Okay. graph models to represent your mathematical equation into pictures. And there are 3 graphs that I would like to introduce. So there are many different types of graphs. I'm going to be talking about probabilistic graphs. Okay, probability. There are 3 graphs that I would like to tell you. There are more other graphs, important graphs, but there are 3 graphs that I would like to introduce to you, and that is directed graph, undirected graph, and factor graph. Okay. So a little bit of introduction to probabilistic graphs, directed, undirected graphs, and then I'm going to relate some. So if you have graphs, there are some benefits. You can see right away what is relevant to you and what is not. So, just example. You want to do well in the exam, on my midterm, and you say, what is important in doing that exam? You can think of a million things. Read the textbook, do homework, may include being nice to me, buying me dinner, and then maybe also that might include also being nice to my wife and being nice to my kids, being nice to my students. Everything is related, it seems. By looking at graph, you really see what is relevant. What is really, really relevant in solving that problem. Okay? So that relates to Markov blankets. So graph, MRF, CRFs, these are undirected graphs. And then one makes graphs. So this graph, what is, so it tells you conditional independence. I'm trying to do well in my exam, my midterm. Other things, if I know something, other things are independent, they're irrelevant. Okay, that's, by looking at the graph, you can see that right away. Another thing is you can do inferencing quite easily by message passing. Okay, by message passing, and I'll tell you what example. You do, everyone has done message passing in this world. And I'll give you an example. But anyways, I have about 15 minutes or 10 minutes, 5 minutes. So probabilistic graph, it's a little bit of probability, okay, a little bit of probability. General graph theory, okay, those things are all combined in doing this, okay. You may say probability, oh my goodness, I hate that. But the probability theory that we need to know is very, very simple things. Bayesian rule, marginalization, subproblem, and I'll tell you this. Very, very easy. Probability. Graph, there are only some varied things. But this, as you put in more graph theory into it, this can be much, much, much more powerful. Okay? And once you do all this, what it leads to, it finally leads to solving an optimization problem. It leads to solving an optimization, gives you a nice optimization. Okay, so you can, so what is the benefit? You can visualize. If you can see that this and this are related, you put a line there. Do you remember mind graph? You've probably seen mine. This is related to that, and that's related to that, and you've all drawn mind graphs before. So by looking at mind graphs, you can see right away what the whole situation is. Very, very easy. Visualize the whole situation. By looking at it, you can probably come up with some new models, if you can see the overall picture. Some insights. Very important is conditional independence. That's what I was talking about. If I want to do well in my math problem, is all the things related? By looking at it, I can see right away those are not related. Only that. And I only need to know this. It tells you that. And by looking at graph, you can easily move around things and make the problem simpler. So probability, this is all you need to know in probability. The sum rule. If you have a joint probability, x and y are happening together, okay, with this probability, okay, weight and height. Now, if I marginalize over y, then I get the probability of x. That's very easy, okay. Product rule, x and y. X and y happening together. It's an x and y. What's that probability? That is, okay, y happened. Y happened with this probability. Then, and probability given y happened, probability of x. Okay? That's the product rule. And we're all familiar with the Bayes rule. And the denominator here is often called the evidence. Okay? It's the probability of the data. And you can write it like this, okay? By the summary. And we also call this, if this is the joint probability, we say that we are marginalizing over the y. Okay? Now, this is a very important summation. Joint probability of y. This we use very, very often. And you may say, what? This is so simple. It's like this. I know this, but I don't know this. Okay? I consider all the possible y's that can happen. And I sum it out. That means I really don't need to find out what y is, because I've considered all the cases. That's a very important concept that you should understand. Okay, graphs. I got about 1 minute left, so I'll just leave it right here, and then I'll stop there. Any questions? Okay, if there's no questions, then okay, 숙제 언제 나가요? 나왔습니까? Okay, so I want to make it very important that some of these problems may be from the past, and if we see that it's a copy of someone else's work or something, I'm going to be very, very strict and give you a 0. Okay? And if you do well in the homework and do poorly also on the exam, I'm going to look at you very, very closely. If you do poorly on the exam, poorly on the homework, because it's your work, but you do better on the exam, I'm going to reward you. I'm going to reward you. If you do poorly on the homework and do well on the exam, then I'm going to reward you. So do your own work.